Ladies and gentlemen, good day and welcome to another session of the Nambani Academy. We are currently busy recording a series of videos for rates of reactions. So this is part 4 of the videos. Kindly watch 1, 2, 3, and 4 for you to be able now to follow on the synergy of concepts that we explained in part 1, 2, 3, and 4. And I should say thank you very much for your support. We highly appreciate as the team, and that now keeps us motivated to record more videos such as this one. So without wasting any time, maybe I should just give you a breakdown of video 1. Video 1 is basically explaining the concepts of rate. Video 2, Maxwell-Boltzmann distribution curve in terms of the collision theory. And then video 3 explains now the effect of temperature and a catalyst combined. So we are going to look into the two last factors, which will be surface area and concentration. So let's dive in and ensure that we do follow. Obviously, later on, we'll still do an exam type of a question in order to close the misconceptions that will probably be there. So without wasting any time, let's go straight into it. Remember now the slides or the notes will also be available on our website, which is www.nambaniacademy. So it's summarized version with emphasis, because we understand that now when you go to a textbook, in most cases, you do not have time to read everything that is on the textbook. So we are trying now to summarize everything nice and easy for you, so that you can be able now to do well in your physical sciences, especially paper 2. Explanation in terms of the collision theory, and we are now interested in increase in concentration on the rate of reactions. Let's first start by saying, if this is my reaction vessel, if this is my reaction vessel, and I'm going to add another one also for the purpose of emphasis. I'll try to have them at the same size, more or less. And now I'm going to say, on this one, I have 2 mole per decimeter cubed. That is now represented by 2 particles, just for the interest sake. Then I am going to have this one with 5 mole per decimeter cubed, which is in terms of concentration. So I'm going to, let's make them purple. 1, 2, 3, 4, 5. Just number of particles, nothing much. Just to emphasize. I know one will say it's going to create a misconception, but I'm putting my head on the block to say this is the best way maybe of explaining the influence of concentration. Because we say bullet number 1 is now increase in concentration. Increase in concentration, comma, increases the number of particles per unit volume. This is very, very, very important. Increase in concentration increases the number of particles per unit volume. So for A and B, my volume is the same, but the concentrations are different. Hence, I have now the 2 and the 5 mole per decimeter cubed. So what did I actually do? I just increased the number of particles. So I just increased the number of particles. What does this say to me? It says, now remember, according to the previous videos, we said particles are always in constant motion. Particles are always in constant motion. So particles being in constant motion, it basically says, where do I have chances of more collisions to take place? Obviously, it will take somehow a very long time for A, or for the particles in A, for them to collide. But with B now, because I have more particles, the chances of colliding are more. Hence, I said, yes, it might look like we are creating a misconception, but the emphasis is when we increase the concentration, we are actually increasing the number of particles per unit volume. This can also be emphasized further by using the equation C is equals to N over V. So the volume remains the same. The only thing that is changing now is the concentration, which influences the number of moles. The number of moles that we associate with the number of particles. Increase in concentration increases the number of particles per unit volume. That is what we need now to understand. So the number of particles becomes more. The chances of collisions becomes more, because now there isn't enough space for them to move around, but they can actually just collide. But remember, for effective collisions to occur, what must happen? They must also have sufficient kinetic energy. So this becomes my bullet number one. So when we focus now on the concentration, hence it says at higher concentration there are more particles per unit volume. Those are the words that the examiners are looking for. More particles with correct orientation, or more particles per unit volume. We can easily add here to say we have more particles with correct orientation and enough, now what? Enough kinetic energy, which is greater than activation energy. That is now very, very important. They have the correct orientation for them to collide, for reaction to take place. At the very same time, they should have now what? More kinetic energy. More effective collisions per unit time, and then rate of the reaction increases. Very clear, straightforward. But the emphasis is the number of particles per unit volume. We must tell the examiner. So when you just say increase in concentration increases the number of particles, no mark. The emphasis is on per unit volume, because the volume here is what will also influence the number of particles we have. It will also influence the frequency at which your particles are going to collide. Remember, the volume is associated now with the container that we have. So the bigger the container, it basically says now the particles are no longer going to have the very same amount of concentration. So the collisions that we are looking for, the effective collisions that we are interested in, the frequency at which now these particles collide is not going to be the same. Increase in concentration increases the number of particles per unit volume. More particles will have correct orientation and enough kinetic energy which is greater than the activation energy. More effective collisions will take place per unit time, and then the rate of the reaction increases. Now remember, we associate the collision theory with the Maxwell-Boltzmann distribution curve. So for the Maxwell-Boltzmann distribution curve, it's easy to understand that our y-axis represents the number of particles. So this, I'm just going to make it 5 mole per decimeter cubed, and I'm just going to make this one 2 mole per decimeter cubed, just for the purpose of emphasis. So it basically says we have now, let me highlight purple. A is going to have now a higher concentration than B. And it basically says you are going to have higher concentration for A, a higher concentration for A, lower concentration for B. The number of particles becomes smaller or less. Hence, now we say more particles will have effective collisions, larger area under the curve of A. That is the reason why it is important to note and understand what it basically means when one says the influence of concentration on the rate of the reaction. So with that being said, it becomes easy for one to understand. It's clear in terms of the collision theory. So we further now move to the effect of surface area on the reaction rate. Now, let's add another beaker. Put it here. Let's add another beaker. Put it next to the other one. For the purpose of emphasis, we try to keep the volume more or less the same. Now I'm going to add this chunk here and then fill it with green. Let me have it here, fill it with green. That's just the solid. And I'm going to do the same, but now I'm just going to add a lot of small pieces of the same thing. Small pieces of the same thing. But now remember, I'm just going to keep everything the same in terms of the mass. We will say this is just 5 grams. This now combined is also 5 grams. So one will ask, which one between A and B will give us a faster reaction? Obviously, the one that's going to give us more effective collisions. This is just a lump, or at times they use words such as granules, or things like a solid. Obviously, the chances of collision are very less because it's just a lump. Will not be having that consistent motion of the objects, or of the particles. So by so doing, it basically says the chances of us getting a reaction are very less. But let's look at B. B, we have a lot of pieces that are forever in constant motion, They usually refer to it as powder. So what will that say? It will say now I have an increased surface area. So on this one, I have now increase in surface area. And what does that say in terms of surface area? It says I have more particles that are exposed per unit volume. I have a lot of particles now that can react, that can collide. But with the lump, I honestly do not have, as it is just a solid lump or a granule that will not have so much greater surface area. So in this instance, I have now a smaller surface area. So now, in terms of collision theory, which particles are more in terms of collisions? Obviously, the particles of P. Why? Increased surface area, always in constant motion, because in constant motion, they'll definitely collide. But remember, they must collide with correct orientation. Hence, now the emphasis here is with a greater surface area, state of division, more particles are exposed per unit volume. So these are keywords. Like I said, they are bolded, that the examiner wants us to be using in an exam. So more particles have the correct orientation or more collisions per unit time. Let's emphasize again, because remember, energy also influences the rate of the reaction in terms of the Maxwell distribution curve or the energy distribution curve. Then we need to add here and say, and enough kinetic energy, which is greater than activation energy. More effective collisions per unit time and rate of the reaction increases. It is basically that. So the Maxwell-Boltzmann distribution curve of a surface area will be the same as that one of concentration. Consider now us having this one as our 2 mole and this one as our 5 mole. Basically, what did we do? We just increased the number of particles. But I have not seen it asked for a very long time. Surface area in terms of Maxwell-Boltzmann distribution curve. We only work with temperature, catalyst, and concentration when we work with Boltzmann distribution curve. So I believe we have exhausted that. I believe we are in a position of understanding how all 4 factors actually influence the rate of the reaction. So with that being said, ladies and gentlemen, thank you very much. Remember to subscribe, remember to like, tell a friend. We are in all platforms that you can think of. Just search for Nambani Academy, and believe you me, you'll definitely get something nice and something relevant. Remember, the notes are also available now on nambaniacademy.com, where you can find a nice set of tools that you can use in order to help you do better in physical sciences and mathematics. So from me to you, thank you very much, and be on the lookout now for part 5 and part 6, where we'll be explaining or doing previous question papers or an exam type of question in order for us to emphasize and clear off all the misconceptions. From me to you, thank you very much for your support, and I hope we meet on the next one.